Hello, everybody. As you're joining, we're just waiting for people to join the webinar. Welcome to the Frontiers in Biostatistics seminar. We will just wait for people to join, and we should be starting right at 1 o'clock. Thank you.
So hello, thank you very much for joining us today. Hope everybody had a great weekend. So I'm Hajime Uno, one of the organizers of this seminar series this year. So today we have a distinguished speaker, Professor Tian. Dr. Tian is a professor at the Department of Biomedical Data Science, Stanford University. He received his SCD in biostatistics from Harvard University in 2002. He did a postdoc for a couple of years at HSPH after that. And then he went to Northwestern University and moved to Stanford in 2008. So he has been working on various methodological research projects like the survival analysis, semi-parametric modeling, resampling method, and also meta-analysis, high-dimensional data analysis, also personalized medicine for disease diagnosis and prognosis and treatment. So today he's going to give us a talk about the restricted mean survival time, so-called RMST. So in survival data analysis, RMST is gaining attention as an alternative to the conventional log-rank hazard ratio approach. One of the challenges when we use RMST in a randomized control trial setting is how to do the interim analysis with RMST. So today he will tell us some solutions. So it's very exciting, right? So I am very excited. So okay, please welcome Professor Tian. So please go ahead.
Thank you, Hajime, for the nice introduction, and I'm very pleased to come to this seminar series, although only online. I mean, I wish I can be in Boston. It's kind of home, have a sense of home for me, because I spent more than 6 years in Boston at Harvard. So really appreciate this opportunity. So as Hajime said, I will talk about the group sequential analysis for RMST in randomized clinical trial. And you might ask questions in the middle if, so I probably will pause a couple of times so that people might have opportunity to pose their question. So RMST is not something new. It's it has been proposed probably 20, 30 years ago, but has been pretty much overwhelmed by hazard ratio based analysis until recently, in the most recent 10 years or so. I think thanks to Professor L.J. and Hajime Uno and others to advocate this very attractive alternative to hazard ratio in analyzing survival data. So let me give you a brief introduction for those who are not very familiar with this concept. So in the randomized clinical trial with survival outcome, the objective is very simple. So we want to compare basically the survival distribution for the distribution of time to events, for example, death or progression between two arms. And so essentially we compare two survival distributions, right? And the time to events is often right-censored. So that's why we do not observe the actual survival. That means we do not observe the actual survival time. Sometimes I only know the survival time will occur after certain time points, which means this survival time or event time was right-censored at a particular point. And the consequence is that the distribution of the survival time is not identifiable over the entire support, oftentimes the case, right? Especially for cardiovascular trial or oncology trial. If not every patient died at the end of your study, then normally we only can estimate the survival distribution within the study follow-up, which is normally smaller than the support of the distribution. So that is essentially the second point. So I want to say that we only can study the survival distribution up to the largest follow-up time, and all the claim about treatment benefit and the patient survival profile has to be restricted within that time interval. So this is a very important but subtle issue we oftentimes ignore in interpreting the result. So hazard ratio is is a very appealing summary about the survival distribution. Essentially, it's defined as essentially the density function divided by the survival function, and intuitively it can be interpreted as the instantaneous hazard or the instantaneous risk of death at next moment, given this patient's survive now. And a common choice for the treatment effect is the ratio of two hazard function, the hazard function from treatment arm, the hazard function from control arm. Because hazard function is a function of time, the ratio normally is also a function of time. But in order to use a single number to summarize the treatment effect, we introduce this proportional hazard assumption. So we assume the ratio of the two hazard function over time actually is a constant. So that means even though the two hazard function itself is not a constant, because if it's constant, that means we are talking about exponential distribution. So even though the hazard functions themselves are not constant, but their ratio is constant. And very luckily, the Cox proportional hazards model can be used to estimate this hazard ratio under this proportional hazards assumption. And the hazard ratio, if is less than 1, that means, for example, the treatment versus control. If less than 1, that means the longer survival, oftentimes means the superiority. In typical randomized clinical trial, if hazard equals to 1, that means they are equivalent. So you can see the hazard ratio is just one way to summarize the difference between two survival distributions and the rule the hazard function. So there may be other ways. So if you think about this problem from the ground, if there's no censoring, how are we going to summarize the distribution? I think most of the people will say we use the mean, right, or we use the median, right? So for example, we talk about the average income or median income or median housing price. We're really talking about the hazard function of the housing price, right? If we talk about the distribution, if we can estimate the entire distribution, we use the average or the mean or the median to summarize the center of that distribution. The problem is if there is a censoring, the mean and the median might not be identifiable or not estimable. That means no matter how big your sample size is, you cannot estimate the mean. Median sometimes is estimable, sometimes it's not, depending on how far you can go in estimating the survival distribution, as we mentioned. But fortunately, we still can estimate the so-called the restricted mean survival time, which is RMST, which is defined as expectation of the minimum of T and tau. So that means if somebody survived beyond tau, we give them the credit tau. If somebody survival time is less than tau, we just give them the T, the actual survival time. We estimate this truncated version of the survival time. And this, so the interpretation of RMST actually is very nice. It's essentially the average survival time during a period, during the time windows from 0 to tau. And graphically, the RMST is the area under the survival function within that interval. And also the RMST is something the closest to the mean, under the restrictions that we cannot estimate the entire distribution. So the RMST, I think there's a lot of work about inference of RMST, which is not very difficult. Based on the observation, the RMST essentially is the area under the survival curve. So RMST can be actually estimated as the area under the Kaplan-Meier curve, which essentially is a consistent estimator of the survival curve. And also you can use inverse probability weighting to estimate the RMST. And it turns out that these two approaches are equivalent. So it doesn't matter which one you want to use. So here is essentially a graphical representation of RMST of two groups. And if you, here we have two Kaplan-Meier curves. And you have two, you can talk about RMST for the first arm and RMST for the second arm up to, for example, in this case, day 4,000, essentially it's the area below the curve. And if you want to talk about the difference between these two survival distribution, a very natural summary is essentially the difference between these two RMSTs. Graphically, that represent the shaded region, the area of the shaded region between these two curves, right? So it's the area between curves. So it's a very nice summarization. And also this summarization is always matches with your graphical summarization of hazard of the survival function. Normally we present two Kaplan-Meier curves, and then we present the hazard ratio and log rank test p-value. So if I give you these two survival curve, I ask you to tell me what is the hazard ratio. Probably, I think at least I cannot tell you. I cannot guess very well what will be the value of hazard ratio in this case. But if I look closely to the graph, I can give a very good estimates about the area between the two curves, which is the difference between two RMSTs. So that means we have a summary really coupled with this Kaplan-Meier summarization or graphical summarization of the two survival distribution. So the inference is also pretty standard, and we try to push this idea for industry folks to use, and also of course for academia investigators to do to conduct randomized clinical trials with survival outcomes. People oftentimes ask us, we like this idea, but how about study design? Can you help me to estimate the sample size? Because we all know the hazard ratio, the sample size estimation for hazard ratio based inference is very simple. You just need to know the number of events, and you can easily even use a hand calculator to backwards calculating the hazard ratio, to calculate the power and the sample size you needed. So for RMST, it's actually not that much more difficult. You just need to write a small program. You probably cannot use a hand calculator to do the sample size calculation. So here I present simple examples without interim analysis, just one final analysis. So if you tell me your hypothesized survival distribution, in this case, I use some historical data to fit two Weibull distributions. I assume the survival distribution actually follows two Weibulls, approximating this two survival curve based on the pilot data. And then, I assume study durations and assume the enrollment period and assume uniform enrollment in this particular case. And also I introduce the loss of follow-up, just people drop off rate. Other than administrative censoring, in this case, I assume it is like a 5%. And then, I specify the type 1 error and the power. If you use hazard ratio based test, log rank test, you will come up with 1,400 patients per arm, roughly. And if you use RMST based test, you can come up with a sample size of 600. In this particular case, because the hazard cross, even survival function approximately cross at the end of the study, so the sample size required if you use RMST will be smaller than that if you use hazard ratio. But if under proportional hazard assumption, these two numbers might pretty close, and hazard ratio based on sample size calculation gives you a slightly smaller number. But this is not the point. The point is that it's pretty easy to calculate this one, and you can compare this sample size with other analysis method. So here's a specific sample size calculation formula for estimating the sample size, and it's messy, but it's not difficult to program as long as you give me the survival function and give me the hazard function and the randomization ratio. I can calculate this one pretty easily. It's just a straightforward integrations. So I will move to the group sequential, but before that, I want to pause here for 2 or 3 seconds, for 5 seconds to see if there's any questions.
Just a reminder to everyone, you can use the Q&A function to ask questions.
Okay, it seems not. So I will just move forward. But oftentimes, at least in phase 3 trials, oftentimes people want to design a study with interim analysis, right, or one or even more interim analysis, which is essentially group sequential design, study design. The purpose is, of course, is for early stopping due to efficacy or futility. So this becomes a pretty standard practice in at least for large studies. And if we want to design a study incorporating the potential interim analysis using RMST, there are some unique challenges. The biggest challenge essentially is the parameter at the interim analysis at the final analysis might be different, because the interim analysis we have a shorter follow-up time, and we might only be able to estimate RMST up to, for example, 2 years. But in the final analysis, we are going to estimate RMST up to 5 years because we have longer follow-up for most of the patients. And that means in the interim analysis, we only can summarize the treatment effect in terms, for example, RMST difference up to 2 years. And in the final analysis, we are talking about RMST difference up to 5 years. So those are fundamentally 2 different parameters, which is very different from the hazard ratio situation. Oftentimes people assume you have a single hazard ratio, at least under proportional hazard assumption at the interim analysis and the final analysis. You have one parameter. Here we have 2 parameters. And if you have more than one interim analysis with different truncation time points for RMST, you may have more than 2 parameters, and they can be all different. And this is the actual challenge for RMST-based group sequential study design. But if you only care about hypothesis testing, actually it's not that difficult. It's fine, even though you are talking about the different parameters at the interim analysis and the final analysis. There was an old paper by Marie and Seatis talking about this topic, and it's a well-written paper. They actually tells you how to conduct hypothesis testing in a group sequential setting, and how to design such a study. So here's a very simple screenshot of that, the proposed approach. So imagine you have a truncation time points at the interim analysis, and you might have a different truncation points at the final analysis. That's tau I and the tau F. They can be, they might or might not be the same. And we also allocate, for example, time point error to the interim analysis and the final analysis. So for example, we can have a 0.01 for interim analysis, 0.04 for final analysis. The total time point error will be 5%. So this is a typical, parameter you need to set before you design the study. And once you have that, once you decide those parameters, the inference or the hypothesis testing in this case becomes quite simple. So at the interim analysis, we will construct, a point estimator for the RMST difference, which essentially is the difference, the area between 2 Kaplan-Meier curves, as I said. But remember, this area is up to tau I, right, which might or might not be different from the truncation time point of the final analysis. Then you can estimate the standard error of this RMST difference at the interim analysis. You can construct the z-test, the what-test statistic, the z statistic, and you can obtain the one-sided p-value very easily because this is just the interim analysis. And under the null, the z is supposed to follow standard normal 0-1 distribution. So you can calculate the p-value at the interim analysis. So if in this case, if the p-value is less than alpha I divided by 2, because this is one-sided p-value, then you will stop the trial and claim for superiority. And if the p-value is greater than alpha I divided by 2, which is, for example, 0.005, then we'll continue the trial until the end of the study. Okay. So for the final, if we continue to the final analysis, we'll be able to re-estimate the RMST difference up to tau f, the new truncation time point we specified for the final analysis. And we use updated data, updated Kaplan-Meier curves, and we can construct a new z statistics. Basically, it's the point estimator divided by its estimated standard error. And then we also can calculate the one-sided p-value. The only trick is that in this case, the one-sided p-value is this z statistics, this under the null, greater than your observed value, but conditional on the fact you did not stop at the interim analysis, right? So if you stop at the interim analysis, you would not go to the final analysis. So you have to condition on this fact. But all those is under the null. So we know under the null, the z statistic at the final analysis and the z statistic at the interim analysis follows a bivariate normal distribution with certain correlation coefficients. And this rho hat is estimable based on the observed data, because in the final analysis, you can estimate the survival distribution up to tau f, right? So with this bivariate distribution, you can calculate this one-sided p-value as the final analysis. So again, if the p-value less than alpha f divided by 2, in this case 0.02, then you can claim superiority. Otherwise, you can stop to say this is a negative trial, right? So you can see for hypothesis testing, it doesn't matter you're talking about the same parameter or not, the interim analysis or final analysis, because all you work on is the z statistics or what statistic, and you might need to estimate their joint distribution, but that is feasible based on the observed data. The true challenge happens if you want to construct the confidence interval in the group sequential study setting. So we all know p-value is not adequate, and we even as a group of statisticians, we even start to condemn the use of p-value, right? Over-interpret the p-value. So I think one simple alternative is not perfect solution, but is attractive alternative is to present the confidence interval and the point estimator coupled with the p-value to provide a global picture of the information about that null parameter. The confidence interval ideally should be consistent with the testing result. That means if you reject the null, the confidence interval should not include the null, right? And in the group sequential setting, the confidence interval can be constructed either at the interim analysis or at the final analysis, depending on the result, right? Because if you stop at the interim analysis, you have to construct the confidence interval at the interim analysis. And if you continue the trial until the final analysis, and then you should construct the confidence interval at the final analysis, which is a random practice, right? So we don't know at the beginning of the study which confidence interval will provide, but we'll provide the confidence interval with your testing result, either at interim or final analysis. And in this case, it's even actual challenge because we're talking about different parameters. But let's review the confidence interval for hazard ratio, which does not have this problem. At least under proportional hazard assumption, we assume the hazard ratio at the interim analysis and the final analysis were identical. So the basic idea to construct the confidence interval for hazard ratio in group sequential setting is to invert a test. For example, in this case, we consider a test theta 0 equal to theta versus alternative theta 0 less than theta. If we reject the null, the theta 0 will be less than theta. We will favor the alternative, and then we have smaller p-value, then we can invert this test to obtain the one-sided confidence interval for hazard ratio for theta 0. So the p-value essentially is defined as the potential result under the null is more extreme than the observed result, right? So we need to define what do we mean more extreme. And actually, I think Butch and also Professor L.J. Wei and also and many others, and they actually have this very nice definition about what do we mean the result is more extreme. So imagine you have two studies, right? You have two results. So so under the null hypothesis theta 0 equal to theta, what do we mean A is more extreme than B? That means if you reject the hypothesis at the interim analysis, if both reject the interim, the null hypothesis at the interim, what do we mean A is more extreme than B? That means the word test statistic at the interim analysis for study A is more extreme than the interim analysis in the word statistic for result B, right? So we have two word statistics. This one is even smaller than this one, and or if A reject at the interim, but B does not. In that case, we also say A is more extreme than B, or neither of them rejected the interim analysis, stop at the interim analysis, but the final testing result of A is more extreme than B. So essentially, if both stop at the interim, the test statistic of A is more extreme than B. If both stop at the final, then the result of A is also more extreme than B. If A stop at the middle at the interim, but B continues to the final, then regardless of the test statistic, we consider A is more extreme, the result A is more extreme than B. So with this set of definition of more extreme, we can calculate this p-value under the alternative. So I won't go to in details, but basically, you can have the joint distribution of the word test statistic at the final and the interim analysis, based on which you can calculate the p-value according to the A is more extreme than B definition we just described in the previous slides. And the confidence interval would be all the hazard ratio value makes the p-value greater than 0.05. That means you cannot reject this particular theta value as a potential hazard ratio value. In this case, this is one-sided confidence interval for theta less than something. Right? So it's very, very straightforward. But for RMST, as we said, there's extra difficulties to deal with RMST because the parameter, the interim analysis and the final analysis were different. So in the interim analysis, we talk about the DI, the RMST up to tau I. And the final analysis, we talk about the RMST difference up to tau F. So these two are fundamentally different parameters because we talk about different time intervals. So what is the solution in this case? I think the easiest solution actually is to construct the confidence region for those two parameters. We are not talking about a single parameter, so we cannot talk about the confidence intervals, but we can construct confidence region for those two. And the procedure is exactly the same. We also need to define what do we mean A is more extreme than B, and we can define the result A is more extreme than B exactly the same way as we did before for hazard ratio based inference. But here, the null is essentially the difference is that the null hypothesis or alternative is not theta equal to theta 0 equal to theta, but the DI equal to DI and the DF equal to DF. So we need to specify this pair of parameters under the null hypothesis and also under alternative. So it's not a single parameter, but otherwise the definition of the p-value is exactly the same. And we still want to invert that test to construct confidence region for this pair of parameters. So again, I would not go to details because this is actually is a pretty standard, although the formula, the expression might look long, but basically you can have the joint distribution of the Zi and the Zf, and then based on which you can calculate the p-value, and then you can invert this test to obtain a confidence region for these two parameters by collecting all the combinations whose p-value is greater than 0.005. Okay, so we can construct confidence regions. Here is just I should skip this. I want to skip this one because this essentially just tells us how can we estimate the correlation coefficients of this rho. You know, this is very standard.
So, can I ask a question?
Sure.
So what happens if the trial stop at the interim analysis? We cannot estimate the F, right? How you construct confidence region?
Yeah, so that is a good question. So actually that has something to do with what do we mean more extreme than A is more extreme than B. If you stop at the interim, then you only talk about if the potential result is more extreme under the null is more extreme than your observed data. That means you only need to consider the potential result also stop at the interim analysis with a even bigger Z statistics. So in that case, you don't need to estimate the correlation coefficients. You still can estimate the p-value without worry about the joint distribution. So I think in summary, if you stop at the interim, only the distribution of Zi matters. Mm-hmm. If you go to the final, you need to estimate the joint distribution in order to calculate the p-value.
I see. Okay. Yeah, thank you.
So here I give you some very concrete examples. So here I simulate some data because the real data is difficult to get. So I simulated the survival time from two exponential distributions. I simulated the censoring time, and everybody truncated year 5, and enrollment is uniform between 0 and 3. So I try to make it as realistic as possible. So at the interim analysis, I talk about the tau I equal to slightly more than 2 years. At the final analysis, the truncation time is close to 5 years, right? So the sample size is 100 per arm, and the true RMST difference at the interim analysis is 0.155, and the true RMST difference in the final analysis is 0.5. It's much bigger than the difference in interim analysis. You can see, you can just look at these two numbers. And I decide to spend 0.01 level at interim, and the corresponding cutoff value of the Z statistic is 2.3. So this is roughly the survival curves looks like. Okay, so in the first simulation, based on the simulated data, I obtain a Z statistic. The interim analysis is equal to 3.8. That means the one side of the p-value is less than 0.01. Then I should stop at the interim analysis according to my allocated type 1 error. Then we can construct confidence region for DI and the DF. But in this case, the confidence region for DI and the DF actually is a confidence interval for DI only because there's no restriction for potential value of DF. So you can see this red region essentially is a confidence region we just mentioned by inverting that particular test. And this confidence region essentially says that RMST difference at IA is greater than 0.25 or something, right? So that essentially automatically give us a confidence interval for DI, although we said we are actually constructing a confidence interval for DI and the DF, but there's no restriction for DF. So we have a confidence interval, and this confidence interval is consistent with your test result because you reject the null, and this confidence interval is above the null. Okay, so this is the simple case and very nice. So the more challenging case is that we did not stop at the interim. We go to the final, right? So I simulate another data set. This is what happened. So in this case, the interim analysis was statistic or z statistic, the interim is 1.17. So we cannot stop. We should go to the final analysis. And in the final analysis, the p-value is 0.021, less than 0.04 actually. And we should reject the null. So here is essentially the Kaplan-Meier curve on the left, you can see. So this two thinker line actually is the Kaplan-Meier at the interim. So you can see these two by random chance, they are just pretty close to each other, although we know the treated arm looks slightly better than the control arm. But if you continue the study, the two Kaplan-Meier curve becomes this thinner line, and they are more separated and more significant, the difference. And in this case, we did not stop it at the interim analysis, but we proceed to the final, and we can reject the null hypothesis from testing perspective. And then if we repeat what we have done for the confidence region, then this will be the confidence region, the purple region. So here is the RMST difference in the interim, and here is RMST difference at the final. So this is the DI, this is the DF. You can see this is the confidence region. Any possible value here combined in this region are possible value for DI and the DF. So you can see this is not very helpful for us to know what is the value of DF, because as we said, in this particular simulated data set, we go to the final analysis, and people want to know what is the possible value of DF. That means we should provide a confidence interval or an interval for DF. But here, the DF can be any value, right? Can be as small as -0.4, can be as big as 0.4. Depending on the value of DI, but we don't care about DI. We only care about DF, right? So that is the challenge. We have a well-defined confidence region, but we don't know the value of DF because this region takes this very weird, inverse L shape. So the remedy actually is surprisingly easy. We just need to construct. We know that the difference of DF and the DI normally is greater than 0 or greater or equal to 0, unless two survival curve cross, right? So imagine, I just go back very quickly for this RMST. You can see the further you go, the difference in RMST should be bigger, right? For example, if you truncated 2,000 times, your region is this one. If you go to 4,000, then the region between two curves becomes longer, right? So the RMST difference should be bigger, unless these two survival curve cross very severely after the interim analysis, which is very unlikely in practice. So, based on that observation, we know DF is greater than DI with a very high chance, but we don't know for sure, right? But based on the observed data, we can construct very like 99.8% confidence interval for DF minus DI, and we expect this interval, this D hat is very likely to be greater than 0 or even or above 0, right? Because we know DF minus DI is greater than 0. So actually, in this case, we construct but this can be considered as confidence region for DI and DF, just taking this special form, right? So we essentially, the remedies, we construct a confidence region of this sort, and also we construct the confidence region, the inverse L shape confidence region we just mentioned. We take the intersection of these two confidence regions, and we still can guarantee 95% coverage, because this one is 95.2, this one is 99.8. And you can see the confidence region suddenly becomes something like this. And then we know what is the DF, what is the possible value of DF, because the smallest the DF value is here, right? So we rule out all the possible combinations of DI and DF in this lag, in this region. So in this case, we can provide a confidence interval for DF, which includes 0. It's not perfect, but not bad, right? That means it's pretty informative. Then we can as we said, we construct confidence region of df minus di, but we also can do it for df minus di times 2 times 3, so or times 0.5. We don't need to consider df minus di because we know we want to downweight di, right? Because we know di is estimated based on less information. So we might want to put some weights here. So you can see with different choice of W0, we have a different intersection with our original like a 7-shape confidence region. And the lower end of DF is quite different. Some of them is pretty high, some of them is pretty low. And turns out if we choose, for example, W0 equal to 1.5 in this case, the confidence region for DF becomes 0.003 and to infinity. That means the one side of the confidence interval is above 0 and is consistent with the fact we are going to reject the null hypothesis in the final analysis. You can see the effect. We intersect with this line, and the resulting lowest touching point of DF is above the 45-degree line, DF minus DI. So if this is corresponding to DF minus 1.5 times DI. Okay, so that means we have some space for improvement if we choose different weights. So here I did some simulation. I would not go to details, but the basic idea is that you can see this is the average position of the lower end of the confidence interval. The W0 equal to 1.5 is indeed the best choice. You should choose something between 1.5 and 2. They give you, the narrowest confidence interval for DF if you stop your trial. If you did not stop your trial, the interim analysis. And in this case, the coverage level is very close to 95%. So that means we do guarantee the coverage level using this method. And this is under the null. And also you can see W0 equal to 1.5 or 2 is the best choice that makes the DF, the confidence interval DF as narrow as possible. And the coverage level in this case is slightly more conservative, but that is expected because we construct the confidence region and we only look at the lowest point for DF or the DI direction. So we actually expect some conservativeness. So probably let me finish the discussion so we can open for questions. So I think there's still some intrinsic dilemmas, right? Because people say, you have 2 parameters. You talk about RMST, but if I do hazard ratio, I only have single parameter, single confidence interval. Why bother? Actually, the problem is that hazard ratio has the same problem. They just did not. We just swept it under the carpet. The hazard ratio at the interim analysis and the hazard ratio at the final analysis might or might not be the same. We assume they to be the same because we have this proportional hazard assumption. But for example, if you stop your study at the interim analysis at 2 years, you never know the proportional hazard assumption will hold for 5 years period, right? Because you simply don't have any data beyond 2 years. So I think the hazard ratio is not immune to this problem. You are still estimating 2 parameters. So probably even for hazard ratio, you should use the method we discussed here to construct hazard ratio, acknowledging the 2 hazard ratio might be different at the interim and the final analysis. That means essentially violation of the proportional hazard assumption. So in our case, we hope DI equal to DF. That means we can tell people, we can present the treatment effect summary with a single parameter, right? RMST difference up to 5 years, for example, not sometimes 2 years, sometimes 5 years. So this is still, I think, presents some difficulty in interpretations. And if there's more than one interim analysis, for example, you do 3 interim analysis, the proposed profile approach becomes very complex and very conservative even, because you need to construct confidence region for 5 parameters rather than 2 parameters, right? So that makes things overly complex and conservative. So there's some possible solutions. I will just go through very, very quickly, especially for this one. I think as I said, people don't like the idea you have 2 parameters, but it is possible, it is the interim analysis, you fit a parametric model, for example, using Weibull, using the data only available at the interim analysis up to tau I. But once you fit a parametric model, exponential, Weibull, log normal, you extrapolate this parametric model to tau F, right? To the planned the truncation time for the final analysis. And then you can estimate the parametric version of the RMST difference because you can do extrapolation, right? So you can estimate this RMST difference. And then you can do exactly the same test. And if you stop it at the interim analysis, you are going to present the treatment effect and the confidence interval for this parameter. Basically, you still claim this is the RMST difference at year 5, but this estimator is based on the Weibull distribution, for example, based on extrapolation. But I only use the data available at the interim analysis. And if you did not stop at the interim and you go to the final, you were able to estimate this RMST difference at the final analysis non-parametrically. You can update your final analysis. You can estimate your final estimate for the RMST difference and make a decision at the final analysis. In this case, you have 2 parameters, 2 parameter estimates. They can be the same if your parametric assumption is correct or approximately correct. So that essentially present 2 options, right? So you can assume these 2 are identical. Then you can use the same procedure to construct confidence interval for hazard ratio under the proportional hazard assumption. But of course, here you have to acknowledge your parametric extrapolation is correct. Alternatively, you don't assume they are equal. So you report the extrapolated RMST difference based on the parametric model at the interim analysis if you stop at the interim. And you report the non-parametrically estimated RMST difference at the final analysis if you stop at the final analysis. But this time, at least you aim to estimate the same RMST at year 5. Just have 2 different estimates. And the first estimates might be different from the second one if the parametric assumption is violated. Right? So this is a sort of a remedy to that problem. Alternatively, you can try different parameters. I don't think we should go through here. And if you have a lot of interim analysis, more than 1, you also can you can simply construct you can allocate the type 1 error to those interim analysis and the final analysis, and then you can simply construct confidence interval for like 1 minus alpha 1 for D1, 1 minus alpha 2 for D2 if you stop it first, if you stop it second, so on and so forth. So it's very simple. You construct a 0.99 point confidence interval for the interim analysis if you stop at the interim, and you construct a 0.96 confidence interval for the final analysis if you stop at the final. So this actually is a very simple approach. You can guarantee the coverage, but this one can be very conservative, at least theoretically. But amazingly, I did some simulation with multiple interim analysis. Actually, it's not super conservative. So this one actually is a very simple approach people can use in practice. You don't need to necessarily use that complex approach if you don't worry about moderate conservativeness in your inference. I think this is the end of my talk. This is a joint work with Professor Hajime Uno and LJ Wei at Harvard. I think you are very familiar with their names. And also this is a joint work with Ying Lu, which is my colleague, and Brian Tsai is my students at Stanford. So I think this is the end of my talk. I think there's a question in the Q&A. So let me try to read and answer these questions. The first question is, has RMST been used as primary endpoint in recent clinical trials? I think the answer is no. I think most of especially for phase 3 trials, people still tend to use the the log rank test, but now people present RMST as a main sensitivity analysis or secondary analysis. I think we just need to push them. We just need to push them further or to educate people more for them to realize the value of RMST. I do believe RMST is no worse than hazard ratio, even just from power perspective. I think Hajime and also Ludwig from Boston University did some empirical study and realized that in most of the cases, based on the real data, the RMST has no less power than the log rank test. So which is a major concern from industry, I think. The second question is, do we have understanding of how to use RMST method in the setting of competing and semi-competing risk? Yeah, that's another good question. Yes, I think yeah, there's a sequence of you can Google this area. I think there's several papers we completed, we finished, and also other group finished to talk about to generalize the idea of RMST for competing risk and semi-competing risk setting. The basic idea is instead of consider the RMST, you consider the time lost due to different causes. For example, you'd say the survival time lost due to cancer death, survival time lost due to cardiovascular death, and the survival time, the RMST survival time. These three pieces adding together in a typical competing risk setting equals to the length of time window. So you have three pieces and you can make inference for each of them if you like, or jointly. The third question is, should we base decision to stop the clinical trial in interim analysis based on predetermined effect size with associated confidence interval based upon clinical utility instead of p-values? Yes, I think so, but I think that's that would be a little bit long way to go, because you always can argue what is appropriate clinical utility, right? And but I think that is a very good idea, and I think we should encourage people to move away from p-value to consider the effect size, whether the effect size is indeed justifying your stopping trial to interim analysis, especially for the interim analysis, because if you stop the trial interim analysis, you potentially lose a lot of information, for example, long-term toxicity, right? So you really need to have a good justification. I think the p-value itself might not be adequate in this case.
Okay, thank you very much, Shirug. It's really nice talk. I very much appreciate it. So so I think we don't have the question in the QA box. So so let me ask a couple more questions.
Hajime, there is a question in the chat.
Oh, chat. Okay. Let's see. No, so can you read? I don't see
Yes.
it.
I can see the chat. Let me read it. I'm frequently tempted to compute confidence interval ignoring interim analysis plan to interpret data. They are precisely interpretable when they are based on asymptotic. What do you think is the main limitation of this lazy approach? Well, I think strictly, I think it depends how do you construct your confidence interval. For example, if you construct your 95% confidence interval at the final analysis, ignoring the fact you did not stop it in your interim analysis, right? So that confidence interval, at least theoretically, might have poor coverage, but in real life, it's not that bad. And actually, I think this lazy approach, if you read these slides, this actually is a sort of a very lazy approach. Imagine we just do one interim, for example, 0.01, and one final 0.04, right? So what you can do is you can simply construct a 96% confidence interval at your final analysis, which is 1 minus 0.04. So if you allocate, for example, 0.04 typepoint error for the final analysis, you reserve 0.04, and you did not stop at the interim analysis. However many interim analysis you planned before the final analysis, you conduct your final analysis you conduct your analysis based on at your final analysis. Then you can simply construct your confidence interval of 96% confidence interval, which actually is a theoretically justifiable confidence interval. And you can guarantee the 95% coverage, more than 95% coverage. And you can, based on this simple observation, you can see this lazy approach, you call it lazy approach, actually could be a smart approach, because we know 96% confidence interval will not be very different from, for example, 95% confidence interval. Even 96% confidence interval can guarantee, maybe even conservatively guarantees 95% coverage. Then the 95% confidence interval will not miss too much, right? So I think this is so this will be a shortcut. You can do that, but I think in the final report, important papers, probably you can construct 96% confidence interval, or using the approach we discussed here. The result probably is not very different from 95% confidence interval, the naive interval, but more justifiable. But have a quick look. I think you can do 95% confidence interval to have a very quick sense, to have a sense of the significance of the effect size of the study.
Yeah, I think we still have more time. So let me ask a quick question. So I have a question about the W0. So I think that must be the pre-specified number, right? Do you have any recommendation about how to choose W0?
Yeah,
I think that's study specific.
Right. I think exactly like you said, I think we should pre-specify W0. We cannot play this game, for example, with one particular observed data. We try different W0 and make choosing the W0 resulted in the highest, lower bound of the confidence interval for DF. So that's why I run this simulation. So this one, for example, is the lower end of the confidence interval for DF, averaging over 2,500 generated data sets. So this is not for one particular data set, but averaging over a big number of similar data sets. I think based on this, the W0 equal to 1.5 or 2 probably is a good choice. But I think this choice really depends on on the particular study design, right? When is your interim analysis? When is your final analysis? Your enrollment speed, or so on and so forth. I think probably in practice, you can, without looking your data, you can simulate. You can basically, using those parameters used for your study design, you can run a simulation, to see what is the best choice of W0, and using that particular W0 in your final analysis.
Okay, yeah, thank you very much. So I think it's time. So do we have any other questions? Okay, I think no more questions. So again, thank you very much for a very excellent talk. Maybe we can close this session.
Yeah, thank you. It's really my pleasure. And bye-bye.
Bye.
Much. Bye. Thanks, everyone.
Thanks for a wonderful talk.
Thank you. Bye-bye.
Bye.